So good afternoon. Now we are going to discuss about three-phase induction motor. So what is a three-phase induction motor and how it differs from a single-phase induction motor? Single-phase induction motor means we have only one phase and neutral, and it is mainly used for lower power application. So in order to have high power application, particularly in industrial application, we are preferring three-phase induction motor. So here we are having three phases R, Y and V. So induction motor, as I have already told you, the rotor receives electrical power by induction. So how it differs from DC motors means, in DC motors the rotor receives electrical power by conduction, whereas the AC motor, that is the induction motor, receives electrical power by induction. So here in induction motor, this works by the principle of rotating magnetic field. So what do you mean by rotating magnetic field? So it is also known as RMF. So RMF is nothing but it is the field or flux having constant amplitude and its axis is continuously rotating in space. That is called RMF. So here in construction of a three-phase induction motor, we have to discuss about stator as well as rotor. So how can we discuss about this RMF means? For example, three phase, we have R phase like this, and Y will be somewhat phase shifted from R, and B will be somewhat phase shifted like this. So take this as R, Y and B. So each phase will be phase shifted by 120 degrees. So if I am taking R as reference and Y will be shifted 120 degrees from R, similarly B will be shifted 240 degrees from R. This is the basic thing. And regarding the construction, we have to discuss about stator as well as rotor. Stator is the stationary part, and rotor is the rotating part. So in general, if I want to, the stator may be either star connected or delta connected. So this is nothing but a star connected structure. It is also known as Y structure. So here you will be having three phases with one neutral. So for R, Y and B neutral. So it may be either star connected or delta connected, means you will be having structure like this. So it is mainly preferred for three-phase, three-wire system. Here it is preferred for three-phase, four-wire system. So star connected is preferred for three-phase, four-wire, and delta it may be three-phase, three-wire. So the stator is nothing but the stationary part, and the rotor is nothing but the rotating part. The stator may be either star connected or delta connected. So delta connected means it will be looks like a delta, and star means you will be having three-phase, four-wire, and delta means it will be three-phase, three-wire system. And I have already told you, the induction motor works by the principle of rotating magnetic field. It is nothing but the field or flux having constant magnitude and its axis is continuously rotating in space. So if I am taking R as reference, it starts from origin and Y is shifted from R by 120 degrees and B is shifted from R by 240 degrees. So that you are having a phase displacement, but magnitude won't change. Only thing, at each and every instant the phase or angle will be changing. That is the main thing we have to consider. That is the basic principle behind the construction of a induction motor, working principle. And here we are having, regarding construction, we have to discuss about stator and rotor. Stator is the stationary part, and rotor we are having two types of rotor. One is squirrel cage rotor Another one is slip ring or wound rotor. So we are having two types of rotor. One is squirrel cage rotor and the other is slip ring or wound rotor. So stator usually made up of laminations. What do you mean by laminations? Similar structures are stacked together or grouped together. That's why it is called. Why we are going for laminations? So laminations are mainly preferred to reduce eddy current losses. Eddy current losses. So laminations are nothing but group of similar structures are stacked together or grouped together. So stator won't be of a single layer and it will be a several group of materials added to it. So similar structures will be grouped together in order to avoid eddy current losses. So stator, we have the diagram we can see. So generally we have a stator like this and we have a rotor. So this is the outermost part, stator. So this is my rotor and both stator and rotor will be placed inside a casing. So to protect this parts we are having outer coverage, that is a casing, and then rotor. So rotor is placed inside the stator. So rotor is placed inside the stator. So here we have squirrel cage type rotor. Why we are calling it as squirrel cage type rotor? So if you see this structure, it looks like the cage of a squirrel. That's why it is called squirrel cage rotor. Here the rotor bars are short circuited with the help of end rings. This is squirrel cage rotor. So in squirrel cage rotor, why we are calling it a squirrel cage rotor? Because the rotor bars are short circuited with the help of end rings. It looks like the cage of a squirrel, so that we can't add any external resistors. So this is called end ring. So we can't add any external resistance in case of squirrel cage rotor. So there is no possibility of speed control in case of squirrel cage rotor. Here the construction advantages of the squirrel cage rotor means it will be construction wise simpler construction, no complication, no different speed control, and also the noise gets reduced. Noise gets reduced in case of and usually the stator and rotor slots are not placed equally and we are having slight skewing. Skewing is mainly preferred to overcome magnetic locking. So to overcome magnetic locking we are having skewing. So in case of squirrel cage rotor, it looks like the cage of a squirrel, that's why it is called squirrel cage rotor. Here the rotor bars are short circuited with the help of end rings, and here we have the construction wise it is simpler in construction, and no, that is noise and all reduced here, and we are moving to, but here for speed control we can't prefer this squirrel cage induction motor. That's why we are moving to slip ring or wound rotor induction motor. So here we have a star connected stator and this is the shaft, and here it is slip rings. So in case of slip ring or wound rotor motor, here we have a star connected stator. So we are having three phases RYB and neutral, and the shaft will be coupled with slip rings. These are all slip rings. Each winding of the rotor is individually connected with the slip rings RY and B. So since it is three phase, we have three phases RY and B, and the rotor is star connected type, and each phase winding of the rotor is individually connected with the slip rings. So that, and here it is the shaft, and the shaft is coupled with the slip rings, and each slip ring is individually connected with the variable resistance. So what is the main function of variable resistance means, if the resistance is high, current will be minimum, so that we can control the speed. So mainly for speed control we are preferring slip ring or wound rotor induction motor, and the rotor is of star connected type. So we have three phase 4 wire connection, neutral is also possible, and we have a common shaft, and each phase winding of the rotor is individually connected with the slip rings and brushes. So what is the main function of slip ring is mainly for speed control, and for collection of current we are having brushes, and we are having variable resistance so that you can have a current control also. If the resistance is high, current is less, like that we can have speed control. So this is the main difference between a squirrel cage rotor and a slip ring or wound rotor. In squirrel cage there is no addition of external resistors, so for speed control we can't prefer squirrel cage. But the advantages of squirrel cage induction motors, it is simpler in construction, less noisy operation and all. But whereas in slip ring or wound rotor we can have many resistances, so that speed control is possible, but the circuit is quite complex. It is a complex circuit. But for speed control we can prefer slip ring or wound rotor motor. Now we can have a comparison of squirrel cage and slip ring motor. So squirrel cage we have, the rotor consists of bars. Here it consists of three phase winding. So in case of squirrel cage, the rotor consists of bars which are short circuited with the help of end rings. So speed control we can't use it, whereas in slip ring we have three phase winding. Here in squirrel cage, simple in construction, it is difficult. So the construction is difficult in case of slip ring. So here in squirrel cage, external resistance cannot be added. External resistance cannot be added. Here external resistance can be added. Here in squirrel cage, slip rings and brushes are absent. Slip rings and brushes are absent. Here slip ring and brushes are present. Slip rings and brushes are present. Here in squirrel cage, moderate starting torque can be obtained. Here high starting torque can be obtained. High starting torque can be obtained. So starting torque is nothing but it is mainly required to overcome inertia. So in squirrel cage moderate starting torque, whereas here high starting torque. Here in squirrel cage rotor resistance starter cannot be used. Rotor resistance starter cannot be used. Here we can use. Cannot be used. Here rotor resistance starter can be used. Starter can be used. Here in squirrel cage rotor copper losses are low because we are not connecting resistance. Here rotor copper losses are high. So here efficiency is higher. Here efficiency is lower. So what is efficiency? It is the ratio of output power to input power. Since here we are not having resistors, the efficiency is higher because rotor copper loss are very less. Efficiency is higher. Here efficiency is lower. So this squirrel cage is used for moderate starting torque application, whereas slip ring is used for electric traction application where we are in need of high starting torque. Thank you. So working principle of induction motor works by the principle of rotating magnetic field. So it works by the transformer principle, mutual induction. Okay, so whenever induction motor works by the principle of electromagnetic induction. So here rotor is stationary and the stator flux is rotating. And stator flux is rotating. So we have EMF induction when we have EMF production in two possible ways. One is stationary conductor and flux is rotating, or we have a stationary rotor with the rotating flux. In any way change in flux occurs. Whenever you have a change in flux, EMF will be induced. So the slip of an induction motor can be given by, it is nothing but ns minus n by ns. So the difference between synchronous speed and the actual speed of the motor expressed as percentage of synchronous speed. So this is the main principle. So the slip plays an important role because usually due to inertia of the motor, the rotor will take some time to catch up with the speed of the rotating magnetic field. Imagine you have three-phase supply given to the stator of the induction motor. So what happens? A rotating magnetic field of constant magnitude but revolving at some angle difference is produced. So here we have a constant magnitude but its axis is rotating continuously. So the stator has a alternating flux, but the rotor won't catch up the speed initially. It will take some time to overcome its inertia, so that the rotor speed won't be same as that of synchronous speed of the stator. So here we have a difference in speed. That's why we have difference in speed. N is the rotor speed and ns is the stator speed. Due to inertia of the rotor, the stator won't catch up with the speed of the synchronous motor. That's why we have slip. This slip concept plays an important role behind the working of a induction motor. That's why we are calling it as induction motor, because this motor works like a transformer principle, like electromagnetic induction. The rotor receives electrical power by induction, and the speed of the rotor will be lesser than the speed of the stator. It won't catch up with the speed of the stator at once, and it will take some time due to its inertia. That is called slip. So what is percentage slip? It is nothing but ns minus n by ns into 100. If you multiply it by 100, you will get the percentage slip. So if I know ns, I can calculate n. N is the speed of the rotor, it is ns into 1 minus s. So ns is the synchronous speed and s is the slip. So the slip values from s equal to 0 to 1. So at the time of starting, speed is 0. So speed is 0 means slip will be maximum, that is 1. So speed and slip are inversely proportional. Speed and slip are inversely proportional. So at the time of starting, speed is 0 and slip is 1. So both are inversely proportional. So next, effect of slip on rotor parameters. So we have to discuss about the frequency of rotor, that is nothing but slip times the supply frequency, because f is the supply frequency, that is 50 hertz, f equal to 50 hertz. So when we give 3-phase supply to the stator of the induction motor, the rotating magnetic field will be produced of constant magnitude and its axis will be continuously changing. So the frequency of the rotor can be calculated by slip times. Why we are calling it as slip times means the rotor is at its stationary part, and to overcome inertia it will take some time. So it won't catch up with the speed of the stationary magnetic field. So it is slip times the supply frequency. So always the frequency of rotor is lesser than the supply frequency. Similarly, the effect of slip on rotor induced EMF. So E2R is nothing but rotor induced EMF under running condition. E2 is the rotor stationary EMF. So it is nothing but slip. So the rotor induced EMF under running condition is slip times the rotor induced EMF at standstill. So E2 is the standstill EMF, whereas E2R is the rotor EMF under running condition. So E2R is the rotor induced EMF under running condition, that is slip times the rotor induced EMF at standstill. Now similarly X2R can be written as S into X2, where X2R is the rotor reactance under running condition. So X2 is the standstill rotor reactance. So what is impedance? Z2R can be written as square root of R2 square plus X2R square. So R2 square plus S into X2 whole squared. So S is nothing but slip. So Z2R is the rotor impedance under running condition. Rotor impedance under running condition. So it is nothing but square root of R2 square plus X2R square, that is slip times X2 square. So R2 is the rotor resistance and X2 is the rotor reactance. X2R is rotor reactance under running condition. Thank you.